I'm Sophia Sim,
I'm Dominic.
And I'm Volantis.
and today we will be talking about the hardness lab that we performed in our material science class.
Alright, to begin with, looking at the objectives for the lab, we were supposed to perform heat treatment on steel specimen, measure hardness using Rockwell tests, as well as Burnell tests, and then we also were supposed to analyze the effect of heat treatment on hardness and correlate hardness with material strength.
Some background that is needed for this lab is to understand why we are doing hardness testing. Hardness testing is important to understand the strength, durability, and performance of a material. There are two main types of tests today. There will be Rockwell test and the Burnell test. The Rockwell test uses depth of penetration from indentors and assesses under specific loads. There are two different types of Rockwell tests. There's the Rockwell B scale and the Rockwell C scale tests. The Rockwell B is for softer materials like aluminum and 1018 steel, and then it uses a ball head indenter for their procedures. Rockwell C is for harder materials like medium carbon steels like 1045 steel, and it uses a diamond head indentor. The Burnell test uses a known load that applies an indentation to the material, and it uses a hard steel ball to make this indentation. For the Burnell hardness equation, you have to understand this equation in order to measure the area that is being tested. Instead of just using the diameter of the indenter, we also use the diameter of the indentation itself. So to describe that, we use the surface area of the spherical cap. Shown on the slide is the equation for H, which shows the difference in the diameters, and then that can be multiplied by pi big D, and then put together to get the final formula for the Burnell hardness.
For our procedure, we started with hardness testing, and we performed the Rockwell B and Rockwell C tests. We used the correct indenter and load for each material. We took 3 readings per sample to ensure the accuracy for each test. Then we calculated the average and standard deviation. For the heat treatment, we recorded initial hardness of the steel samples we did before, and we heated the specimen to target color using the furnace. We then removed and quenched the samples in water and oil, and then we cleaned off the oxidation layers using sandpaper. We performed the hardness testing again on the above specimen.
Here is the data collection from the Rockwell tests. Above you can see the chart and a bar chart describing the materials and a comprehensive table below. From the bar chart, we can see the differences in the Rockwell B highlighted in blue and Rockwell C test highlighted in red. 1018 untreated steel was the highest strength of all of them tested under Rockwell B. However, when it was air treated and tested, it was slightly lower. And then also when it was air treated and tested using the Rockwell C test, the strength hardness was very low, showing the importance of using the correct test for certain materials. Overall, the aluminum had the lowest strength of them all, which makes sense due to its ductility.
For the data collection for the Burnell test, we have 3 formulas. The one up top shows how to calculate the BHN. The one to the right shows how to calculate the depth of penetration, and the one to the left shows how to calculate the tensile strength. This chart here shows the table shows how we calculated all of the above stated formulas, and we calculated the average of each test. The data analysis for the Burnell test, for the hardness, we averaged it out and we measured it at 64.9 BHN, and this falls under the hardness for multiple aluminum alloys, which is from 20 to 160. For the tensile strength, the calculations for this estimate was around 227 MPa. Comparing these calculated values to other common aluminum alloys, mostly matched the 6061T4 aluminum alloy, which has a 65 BHN and a 241 MPa value for the tensile strength. The BHN values were almost identical, while the tensile strength was slightly different. The difference could be due to experimental factors such as accuracy in measuring the indentation of the diameter or other surface conditions.
And then once again, to finally conclude everything, we performed Rockwell B and C and also Burnell hardness tests on different metal samples, including steel and aluminum. We also looked at significant differences in hardness between heat-treated, untreated, and quenched materials. Aluminum was able to show lower hardness values, while the steel showed higher values, especially after quenching. Water quenching produced higher hardness than oil quenching due to the faster cooling process. Calibration blocks confirmed that testing equipment produces accurate and consistent readings. And finally, we were able to demonstrate the importance of selecting the correct hardness scale based on the material and its hardness range. And future work and things we can change to do better is try out more materials such as stainless steel, brass, and titanium alloys. Use Rockwell C more, or even Vickers scales for more higher hardness values to avoid exceeding the B scale limit was another option. And then performing more trials to improve or have a smaller percentage error. And then finally, using digital tools for more precise Burnell indent measurements and reducing human reading error was another option.
These are the references that we used. Thank you for listening to our presentation.